All right, so in this video, we're going to look at isomerism, and this is going to be on your page 113. I can't believe we've gone that far. So we've learned some of the skills in order to name and draw molecules, and now what we're going to do is we're going to use those to apply it to something called isomerism in organic chemistry. There are two types of isomerism that you need to be aware of: structural and stereoisomers. These things are not very easy to understand, and they do take practice. I think what I'm going to do is I'm going to take you through some of the basics of isomerism, how and why it exists, and then we're going to go through some actual examples of what you might be faced with when you're given an exam question like this. So for structural isomerism, it's a compound that has the same molecular formula but a different structural formula. So let me give you a very quick example of what this might look like, and I'm going to use butane as the example. So let's have a look at butane. And we know that the molecular formula for butane, which is a straight chain, is just going to be C4 double it, add 2 is H10. Now I can draw butane with 4 carbons like this: 1, 2, 3, and 4. And that is the molecular formula for butane. However, there is an isomer that exists of C4H10. And what we mean by that is there any other way to draw C4H10? And there is. And what we can do is we can do something like this. So we go 1, 2, and 3, and then we add the 4th carbon here. And this is no longer called butane. It is C4H10, but let's go back to our nomenclature, and you should be able to do this by now. So I'm going to go 1, 2, 3. That's my stem, so that's prop. No double bonds, so it's going to be ane. And you can see over here, I have a branch. And how many carbons are in that branch? 1. So I call this methyl propane. So methyl propane has the molecular formula C4H10, and butane also has the molecular formula C4H10. These have the same molecular formula but a different structural formula, or a different structural arrangement. There are 3 types that you need to be aware of. I'm going to stick very closely to chain isomerism, and if we come across positional and functional, I'll explain and teach it you as we come across it. But chain isomerism is the main form you need to know. What you can see in the example I've done is we have actually changed the chain. So for C4H10, we've got butane, which is a 4-carbon chain, and then we've got methyl propane, which is a 3-carbon chain. There are 4 carbons, but there are 3 carbons in the chain and 1 as a branch. So it's a 3-1, basically. In order for it to be an isomer, they, 1, need to have the same molecular formula, so that's C4H10. And 2, this is the best part, they need to have different IUPAC names. So when you go to name the molecule correctly, it shouldn't have any similarities to the name before. So this won't ever be called butane, and the methyl propane is exactly its own thing. Let's give some more examples and be a little bit more clear. I think the example that I'm going to show you a method that I use for chain isomerism. I would like you to use that same method to determine the answers to this question, but just watch how I go through this. So for chain isomerism, hydrocarbons can either be branched or unbranched, and that's what we're going to be looking at right here. The question is, draw and identify all the structural isomers of the following molecules. So for anything that has 6 carbons and 14 hydrogens, what could this look like? The strategy that I do for this, so when you've got structural isomers and you're given a molecular formula, we start off with the highest possible carbon chain. And that is identified there, which is 6. Let's draw a 6 carbon chain to start off. 1, 2, 3, 4, 5, 6. And then I like to double check edges and corners. 1, 2, 3, 4, 5, and 6. So I've got 6 carbons there, 6 carbons in a row. I'm going to call that hexane. Now the next trick, this is the way that I like to do structural isomers. It will work for you, it will take some practice, but now we're going to look at a branched isomer where we have 5 carbons plus 1 branch. I'm not going to keep that 1 in red. So if we call this 5 plus 1, and that is where we're going to start with it. So with 5 plus 1, I'm now going to draw a 5-carbon chain. So I'm going to go 1, 2, 3, 4, and 5. And then I've got 1 branch that needs to stick out, and because I've got an iPad, I can show you that I can put this in different locations. Now, to give you the clue already, I can't put this branch at the end of a chain. If I do, it becomes hexane again. You watching? If I put it at the start, oh my god, it's the same as hexane. And then if I put it at the end, oh my god, it's the exact same thing. So, wait, there we go. And it's the exact same thing, and it does not work like that. So, the only places you can put it is on this middle carbon, so the carbons that are adjacent to it. Let's put it on this carbon number 2 over here first. So, that works. And there is one of the isomers. Now, if I duplicate this, because I'm lazy, where else could I put this branch? Yeah, I could put it here as well. Is that the same thing as the one above it? No. The branch is in a completely different place, and it will have a different name when I go back and name it all. Can I put it anywhere else? So let's duplicate this one more time. And this time, you might think I can put it here. However, that is the exact same thing as this. It's the exact same thing. And if I can just maybe put it there and rotate this, you can see that it is basically just the exact same thing. It's just slightly arranged differently. So there are only 2 isomers that have a 5-carbon chain. Now we're going to do it again. We're going to go 5 plus, and this is where it's different. I go 1 plus 1. Still equals 6, so I've still got 6 carbons, but now I'm going to look at anything where it has a 4-carbon chain with 1 and 1. And this is the strategy that I use. So 4 carbons in a row, I'm going to go 1, 2, 3, and 4. I'm going to add 1 branch. So where can I put that branch? Not at the start, not at the end. I'm going to put it on carbon number 2. Let's duplicate this, because I've still got 1 more branch to assign. Again, I can't put this at the end or at the start, because then that's the same as one of these guys. But over here, I could put it on this carbon here like that. And there we go, 4 and 1 and 1, and that works. Let's duplicate it and see if I can do this again. So I've got 4 carbons in a row. Let's move that branch, move that branch. Right, where else could I put these? I can put it back on carbon number 2, and then I can put this one also on carbon number 2. The main reason being is carbon can have 4 bonds, and there we go. And that is not the same as the one above. Can I do this again? Let's duplicate one more time. Don't worry, I will get less repetitive with this. I'm going to break the parts. So I've got the stem, 4-carbon stem, and now I'm going to put it 1 here and 1 here. And now you can see this looks completely different to any of the other ones that I've got, but it is not. So do not draw this one out. Let me name them and show you why the naming part is really important. So let's start by naming this one. If you want to pause the video and have a go at it yourself, you can do, and just double check that you got the same name as me. That would be awesome. For those of you that are just going to continue watching the video, then, well, let's just go through it now. So I'm going to go 1, 2, 3, 4. I've got 4 carbons in a row. I call this bute. No double bonds. I call it ane. However, I've not identified the branches. I've got 1 branch here and 1 branch here. That branch has 1 carbon in it, and this has 1 carbon in it. So I've got a methyl over here. So I've got a methyl on carbon number 2, and I've got a methyl on carbon number 4. So I've got 2 methyls. The way we name this is dimethyl. So this is dimethyl butane. Now, what else is important is where those methyls are. The first one is on 2, so I'm going to name this one 2, 4 on 2, 3, sorry, my apologies. 2, 3 dimethyl butane. And that's the name for this guy. Let's have a look at this one then. I'm going to go through this one a little bit quicker. Got 4 carbons in a row, we call it bute. No double bonds, I call it ane. I do have methyl groups. I've got 1 here and 1 here, and that is also going to be a dimethyl butane. Now, is that the same name as the one above? Yes. Have I numbered it correctly though? No. We number it on the lowest number of carbons. So I can go 1, 2, 3, 4, and then that would be 3, 3 dimethyl butane. Or I could do 1, 2, 3, 4. What's the lowest number there? 2. So the first methyl group is on carbon number 2. So over here you can see watch carbon number 2. Whereas the next methyl group, that is also on carbon number 2. So it's actually 2,2 dimethyl butane. And then let's have a look at this one. Again, I'm going to try and speed through this one. 4 carbons in a row, oh god, bute, no double bonds, ane. 2 methyl groups, 1 here and 1 here. So that is a dimethyl again. But the numbering, we're going to go 1, 2, 3, and 4. And if you're thinking this is 3, 3 dimethyl butane, you're wrong. Because this is going to count from this side. 1, 2, 3, and 4. This is the lowest number of carbon, is the lowest chain is the lowest chain for the methyl groups to be on. So this is going to be a 2, 2 dimethyl butane. These two are the exact same thing. They've just drawn them differently. That's it. So the drawing doesn't actually matter, but the naming will show you that they are different or not. So let me clean this up. I'm just going to go back in time and reverse all of those things. So when I eventually clean this up, you'll see that for C6H14, there are actually only 6 isomers for it. Although now I've seen 5. There are 5 isomers for it, sorry. I've got hexane, I've got the ones with the 5 here, and the ones with the 4. If you want to have a go at naming the 5 ones as well, that'd be awesome. But in the meantime, what I'd like you to do is, can you circle the 3 different isomers of pentane? Remember to use the naming method to make sure that you get this right. Right, let's move on. We're going to look at the other stereoisomer, and again, there's quite a lot that goes into stereoisomers, but I just want to teach you some of the rules just so that you can engage with the activity first of all. So stereoisomerism is slightly different to structural isomerism. So structural isomerism, we're looking at the same molecular formula but a different structural arrangement. For this one, we're saying it's compounds with the same structural formula but a different arrangement of atoms in space. So not only do these have almost the exact same structure as each other, but they now arrange themselves differently in space. And that sounds really weird when I say it out loud. I'm going to tell you the rules, and then I'm going to show you the examples, and then it'll make a lot more sense, and then we'll go back to the rules one more time. So the first thing, in order for something to have stereoisomerism, so it must be possible, we, 1, need a double bond that restricts rotation. That is 1 mark in your exam. Number 2, and this is the hard one, 2 different groups attached to each carbon in the CC double bond, and there's your second mark and your second rule. Now, let me explain that very, very quickly. Let's go to the very basics. I'm going to draw ethene. So I'm going to draw it like this. Let's give it 2 halogens. So I'm going to do a Cl there. I'm going to do a Cl there. And if we do this with mods in class, you will see it's going to be very, very different. Let's look at the rules. Number 1, does it have a double bond that restricts the rotation? Yes, right there. Number 2, does each carbon in the double bond have 2 different groups attached to them? Let's have a look at that. Carbon over here, is it in the double bond? Yes. Does it have 2 different groups attached to it? 1, 2. Cl and H are not the same, so yes, that does. Highlight this one. 1, 2. They're also different groups. Now, yeah, they're the same as this carbon's, but for that carbon in particular, these are different. So this can have stereoisomerism. And there are 2 types of stereoisomerism that we are going to look at. You may see E and Z, and we can talk about that in class. But for now, we're going to use cis and trans. These are terms that are socially, politically charged, but that you might be a bit more familiar with, and they do still have the same Greek derivation. Cis is to mean the same on the same side. Trans is to mean opposite or different. So it's on the different side of where they are at. Now, when we look at this isomer, what we're comparing is the groups that are similar on the opposite side. So over here, I'm looking at this side compared to this side. And then what I'm looking at from there is, how is this chlorine related to this chlorine? Or how is this hydrogen related to this hydrogen? So for carbon number 1, this guy, is the hydrogen pointing up or down? In this one, hydrogen is pointing down. But over here, is that hydrogen pointing up or down? It is pointing down. Are those arrows pointing in the same direction? Yes. So that is cis. So that is a cis isomer. And then we can name that using our nomenclature from earlier on. Now, in order for me to show you the trans isomer, I would have to break the bond, rotate the middle bond, and then reform the double bond, which just isn't going to happen. So it has to be a brand new molecule. Let me break this apart like this. Stick a hydrogen there, and there we go. We've got a completely different molecule now. And you might be thinking, yeah, but it's got the same number of things. Yes, it does. But it's going to have a completely different name. The way we name it is, now, does it have a double bond? Yes. Carbons, we already know. So let's have a look at the hydrogen. This time, hydrogen is pointing upwards, but this hydrogen is pointing downwards. Are they pointing the same direction? No, they are not. So that is our trans version. And that is how we're going to be able to identify our cis and our trans. You focus around that double bond, you have a look at the direction the groups are pointing, and then you draw them out. What I've got for you here is an example of a stereoisomer where you need to draw them and name them. I've got this over here, which is our molecule. So this is going to be the name in general, but how do I name the cis version and how do I name the trans version, and vice versa? Remember, if it's cis, we have the cis at the start, and if it's trans, we put the trans at the start as well. What I would like you to do is, using either displayed or skeletal, I don't mind which way, can you draw the cis isomer of this? And then for the 2,3-dichlorobutene, this one, can you draw me the trans version of this? And then once you've done that, can you name them for me? Have a go at this. We will have more practice in class, and when you see this more and more, it'll become more familiar to you. Otherwise, enjoy.